Hello everyone. Welcome back to MP Coding and our Linux device driver development series using Raspberry Pi. Starting from today, we are entering Section 5, Concurrency and Synchronization. In this video, we are going to talk about kernel threads. But before we dive into kernel threads, let's first briefly understand what a process is. A process is simply a running instance of a program in user space. Each process has its own virtual memory space. It has its own user space stack and heap, its own file descriptors, its own security context, and it can contain one or more threads. For example, the Bash command line, the Firefox browser, or any other application running in Linux. All of these are processes. So whenever you run a program, the operating system creates a process for it. Alright, now what is a thread? A thread is the smallest unit of execution inside a process. Inside a single process, you can have multiple threads. These threads share the same memory space. That means they share global variables, the heap, and file descriptors. However, each thread has its own stack and its own CPU context, meaning its own registers and execution state. So you can think of a process as a container, and threads are the workers inside that container. Now let's talk about the difference between user space threads and kernel threads. User space threads are threads created inside a user application. For example, pthread in C, std thread in C++, and threads in Python or Rust. These threads run in user space. They cannot directly access hardware. They cannot access kernel memory. And whenever they need to interact with the operating system, they must use system calls. The Linux scheduler decides which thread runs at any given time, but the execution itself happens in user mode. Now, let's move to kernel threads, which we usually call kthreads. Kernel threads run entirely in kernel space. They do not have user space memory. They can directly access kernel APIs. They can interact with hardware. And they can sleep or block just like normal processes. Here also, the Linux scheduler manages kernel threads just like it manages processes. So both user space threads and kernel space threads are scheduled by the same Linux scheduler. The main difference is where they run and what they are allowed to access. Alright, here I have summarized the differences between user space processes and kernel threads in this table. You can go through it in detail in my GitHub repository. Now, let's understand where kernel threads actually live. Kernel threads exist only in kernel space. They have their own task_struct, just like normal processes, and they are visible in the process list. If you look carefully, kernel threads usually appear inside square brackets. For example, now if I run the command ps-ef, we can get a snapshot of all active processes currently running on the system. And inside that list, you will also see kernel threads, typically shown within brackets. If we run the top command, we get a live, continuously updating view of all active processes in the system. Again, kernel threads will appear there as well, mixed together with user space processes, because from the scheduler's perspective, they are all schedulable entities. Now, here is a very important concept. Kernel threads are scheduled just like normal processes. Even though they run entirely in kernel space, they are still managed by the same Linux scheduler. They compete for CPU time. They have priorities, and they can be preempted, just like user space threads or processes. So from the scheduler's point of view, everything is simply a schedulable task. Now the next question is, why do device drivers use kernel threads? Device drivers use kernel threads when they need continuous background processing. For example, periodic hardware polling, long-running kernel tasks, blocking operations, or continuously monitoring hardware state. Some common real-world use cases include sensor data polling, firmware communication, DMA buffer management, and periodic health monitoring. Now let me give you a simple mental model. Think of a process as a container. A thread is a worker inside that container. And a kernel thread is a worker that lives inside the kernel building, not inside the user space building. That's the main conceptual difference. Alright, now let's move to the coding part. Here, I have created a new make file and a new source file for this example. Inside this source file, I've added the basic module structure with empty init and exit functions. As you can see, this is just the standard skeleton for a Linux kernel module. We include the required headers, define the module license, author, and description, and then define the initialization and cleanup functions. To implement a kernel thread, we first need to include the linux/kthread.h header file, because that provides the kthread API. Now, inside the init function, we are going to create a new kernel thread. For that, we use the helper function called kthread_on. If we look at the definition of kthread_on, we can see that it requires 3 parameters. First, we pass the entry point function. This is the function that the kernel thread will execute. Second, we pass a data pointer. This pointer will be forwarded to the thread function, so we can pass any private data we want. And third, we pass a printf style name for the thread. Internally, this kthread_on creates the kernel thread and wakes it up. If everything is successful, it returns a pointer to a task_struct. If something goes wrong, it returns an error pointer. So before calling kthread_on, we need to implement the entry point function for the thread. If you explore deeper, you'll see that kthread_on eventually calls kthread_create, which then calls kthread_create_on_node. And from there, we can clearly see that the thread function must follow a specific format. It must accept a void data pointer and return an integer. So now, let's implement this thread function. Inside the module file, I'll create a static int thread_ function, and it will accept a void pointer data parameter. For now, we'll just make it return 0. Later, we'll add the actual loop logic. Next, I will pass this thread_ function as the first parameter to kthread_on. The second parameter is the data pointer. Here, I'll create a static integer variable called t1, and I'll initialize it to 1. Later, I'll show you how to use this data inside the thread function. In real drivers, you might pass a private device structure here, but for this simple example, I'm just passing an integer. Then we pass the address of t1 to kthread_on. Finally, we provide a name for the thread. I'll set it to kthread_1. And that's how we create our first kernel thread. Now, as we discussed, kthread_on returns a pointer to a task_struct. So we need a variable to store that return value. For that, I'll create a new static pointer of type struct task_struct, and I'll name it thread_1. Then I assign the return value of kthread_on to this pointer. This call will create the kernel thread and immediately wake it up, so it starts running. Now, very important, we must always check for errors. If kthread_on fails, it does not return null. Instead, it returns an error pointer. So we need to use the is_err macro to check whether the return pointer contains an error. If it does, let's print an error message failed to create thread 1. Then return the actual error code using the ptr_err macro. To use this error macros, we need to include the linux/err.h header file. Now I'm going to copy this kthread_on section and paste it one more time to create a second thread. I'll rename it to thread_2, and this time I'll pass t2 as the data argument. Change the thread name to kthread_2. And update these also. At the top of the file, I also need to declare the new variables, another struct task_struct pointer thread_2, and a new static integer t2. I'll set t2 to 2 to indicate that this is the second thread. Of course, I'll also update the error message to reflect that this is thread 2. Now here is something important. If the second thread creation fails, the first thread is already running. So we must clean up properly. In that case, we need to stop thread 1 before returning from the init function. For that, we use kthread_stop and pass the pointer to thread_1. This is very important. We must not leave a running thread behind if module initialization fails. If both threads are created successfully, Then we print a message indicating that both threads are running. Now let's move to the exit function. When we unload the module, we must stop all running threads. If thread_1 is not null, I'll call kthread_stop and pass thread_1 pointer. Similarly, if thread_2 is not null, I'll stop that one as well. Finally, I'll print a message indicating that all threads have been stopped and the module is unloaded. In the init function, we created 2 threads. But, up to this point, we still haven't implemented the actual thread_ function. So let's implement that now. First, I'll print a message to indicate which thread has started. Remember, when we created the thread, we passed an integer as a void pointer. So inside the thread function, we need to cast that pointer back to an integer. So I dereference it like this and store it in a local variable called thread_id. Then pass this thread_id to print the message that indicate which thread has started. For thread 1, this t1 value passed to here as thread data, then print with this message. For thread 2, this t2 will pass. Next, let's implement the main loop of the thread. We use a while loop and check kthread_should_stop. As long as no stop request has been made, the loop continues running. To avoid busy looping and consuming 100% CPU, I'll add a sleep call. Here I use ssleep and pass the thread_id, so if the thread ID is 1, it sleeps for 1 second. If the thread ID is 2, it sleeps for 2 seconds. Here before the sleep call, I'll print a message indicating that the thread is running. I'll also create a local counter variable and increment it on every iteration so we can see how many times the loop has executed. And I will print that counter value also with print message. This makes it easy to visually distinguish both threads in the log output. When kthread_stop is called, kthread_should_stop will return true, the loop will exit, and we print a message indicating that the thread is stopping. And that completes our kernel thread implementation. Now, one important thing to understand here. When we create these 2 threads, we are using the same thread_ function as the entry point. But even though the function is the same, each call to kthread_run creates a separate thread instance. That means each thread has its own execution context, its own stack, and its own independent runtime state, even though they are executing the same function. So effectively, we get 2 different instances of execution from the same function. Of course, we could also use 2 completely different thread functions if we wanted to. That is totally fine. But for simplicity in this example, I'm using the same thread_ function and just passing different data values. Then inside the function, I print the thread ID to distinguish between them. This keeps the example simple while still clearly demonstrating how multiple kernel threads work. Alright, I have opened the dmesg buffer in another terminal so we can monitor the kernel log messages in real time. Now let's first build the module. I'll type make and press enter. Looks like we have an error saying that ssleep is missing. That means I forgot to include the proper header file. The ssleep function is defined in Linux/delay.h. So let's quickly add that header. Now let's build it again. This time, the build is successful. Now let's load the module and see what happens in the kernel log. Alright, you can see in the dmesg output that both threads have started and are running. The counter value is increasing. Thread 1 runs every 1 second, and thread 2 runs every 2 seconds. Now let's unload the module and observe what happens. You can see that it takes a little time to unload. That's because the threads are sleeping. The kernel waits for the current sleep cycle to finish before stopping the threads. If you look closely in counter value, even though both threads use the same thread_ function, each thread has its own independent execution context. That means each thread has its own stack memory. The counter variable inside each thread is independent. They run separately, even though the function code is the same. That's all for today's video. Today, we discussed Linux kernel threads, how to create them, run them, stop them properly, and how the thread loop works inside the kernel. In the next video, we'll dive into wait queues, poll, and fasync in the Linux kernel, very important concepts for driver development and asynchronous notification mechanisms. So stay tuned. If you found this video helpful, please subscribe to the channel and hit the bell icon so you don't miss upcoming videos. Thank you for watching, and I'll see you in the next video.